Hello students, welcome to Sri Jayendra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 8 of a unit semiconductors. So let's begin with today's class. In today's class we are going to discuss first a logic gates. So let's discuss with logic gates. We can say a logic gate is an electronic circuit which performs a particular logical function. And these electronic circuits are of two types. They are the analog circuits and the digital circuits. So this is divided, or this is differentiated into the two kind of circuits. They are the analog circuits and the digital circuits. The analog circuits is the waveforms are continuous and range of values of voltages are possible. So let's understand that this is the 0 volt, and let's suppose this is the plus 5 volt, then, and let's say this is the minus of 5 volt. So this can vary from plus 5 volt to minus 5 volt, but from plus 5 volt to minus 5 volt it can contain infinite number of voltages. Within this range it can have infinite number of voltages, because if I ask that what is there between plus 5 and minus 5, you will start telling me that sir, it's a plus 5, plus 4, plus 3, plus 2, plus 1, 0, minus 1. I will say no, it is plus 4 and plus 3. Even so many terms would be there, it would be a plus 3.5. Then you will say yes sir, it's a 4.9, 4.8, sorry, 3.9, 3.8, 3.7, 3.6 and something. When I say when it's a 3.1 and 3.0, it's a 3.05. So like such as there is an infinite number of voltages can be possible when we are discussing about the analog circuit. So ranges would be always there, upper range and lower range, it would be always there, but even though within that range, there are infinite number of samples can be available. Now let's look at the digital circuits. They are the waveforms are pulses, and only discrete values of the voltages are possible. Let's say this is the 0 and this is the 5. So if I say there would be a two values only, then it could be either 0, it could be either 5. We could not have anything between this. No 1 volt, no 2 volt, no 3 volt, no 4 volt, no 5 volt. Either it would be a 0 or it would be a 1. So this is what we are talking about, the logic gates. That is the finite number of voltages or any quantity can be possible within given range. Yes, while in the case of the analog circuits, there are the infinite number of pulses or infinite number of voltages can be considered. And when we talk about the digital circuits, only the finite number of voltages are possible. So this is the situation, this would be the situation. And when we say digital, only finite number of samples could be there. For the analog, it would be an infinite number of circuits could be there. So a digital circuit is an electronic circuit in which the current and voltage signals have only two levels, either on or off. And in the above digital signal, the voltage at any time can be either 0 volt or 5 volt. And the digital circuits make use of binary number system, according to which 0 volt and 5 volt values are denoted by the level 0, which stands for low, and 1 for the high respectively. So in the digital circuits, only two levels of the input and output voltages are possible. And the basic building blocks of the digital circuit are known as the logic gates, since they perform logical operations. Generally, the level 1 or high level is at approximately 4 plus minus 1 volt, or level 0 or low level is at approximately zero point 0.2 to approximately 2 volt. So let's begin our study with the logic gates. So basic, or this are the known as the primary logic gates. They are the three logic gates are there that we call as a primary. They are the OR gate, AND gate, and NOT gate. Let's discuss and understood one by one what is the OR gate, AND gate, and NOT gate will behave like. So let's look at first quick questions. We can say a logic gate is an electronic circuit. A logic gate is an electronic circuit which perform a particular blank function. Yes, it is there to perform certain logical functions. Next, when the waveforms are blank and only discrete value of voltages are possible, then such type of circuits are known as the digital circuits. Yes, the answer would be the pulsated. Now, before we begin our study, first we need to discuss certain uh, part of the maths, but it is very interesting maths, believe me. It's a Boolean algebra. Exactly, it could not be covered into the maths as well. Yes, this is a certain different world of the maths. Yes, and that is what we call as a Boolean algebra. Maybe you have studied this in your computer subject, because binary system is there, and in the binary system also this Boolean algebra has been taught. So let's have a look. First, let's understood certain word. It's a truth table. It is a table that shows all possible input combinations and the corresponding output combinations for a logic gate. That is what we call as a truth table, which always speaks truth. Yes, a Boolean expression. It's a George Boolean invented a kind of algebra which deals with logical statements that have only two values. They are namely either a true or a false value. So this is what we call as the Boolean algebra. So these are the certain postulates and theorems of the Boolean algebra. Look at this. This all are the OR laws. When and when they are OR, it has been represented by this plus sign. And when this is the AND, it has been represented by dot sign. It's a complementary, it's a bar. So when I say A or 0, then the answer would be A. When I say A or A, the answer would be A. You just note this down and keep this writing. Yes, and once we are done with the logical gates, you will definitely understand the meaning and applications of this. It's an A plus 1 would be equals to 1. It's a A plus A bar, which would be equals to 1. While we use the AND laws, it is the A dot 0. They are the 0. It's a dot A, which is equals to A. It's a dot 1, which is equals to A. And A dot A bar, which is equals to the 0. And complementary laws, they are the 0 bar would be equals to 1. 1 bar, which is equals to 0. And it's an A double bar, which is the A double bar, which A is equals to the A. So these are the complementary laws. Next, it's a commutative laws, which says that A or B would be equals to B or A dot B, which is equals to B dot A. Even it will follow the associative laws, which is A plus B plus C, that A is equals to A plus B and plus C, that means the OR operation of A and B. And the next, the answer of this will be having an OR operation with the C. Same way, it's an A and B and C will give me an A and B, and answer of this will be having an AND operation with the C. Even it will follow the distributive laws, and it's an A and B or C, which is equals to A and B, or A and C. It's a A or B and C. Then it could be written as A plus B, that means A or B, and A or C. This is the distributive laws. Absorptive laws, it's an A plus A dot B, that is equals to A, and A dot B plus 1, that is equals to A again. It's an A plus A bar dot B. It's an A plus A bar dot B will be the A plus B, and it's an A dot A bar plus B will give me the A dot B. And last but very very important, at least you need to remember this four, at least. These are the De Morgan's theorem, which says that it's an A plus B whole bar, which is equals to A bar dot B bar, and A dot B bar, which is equals to A bar plus B bar. This A bar plus B bar whole bar will give me the A double bar dot B double bar, which tends to A dot B, or I should say A bar dot B bar whole bar. Then it would be an A double bar plus B double bar, which is equals to A plus B. Please note down this. Have you noted it? Have you? Did you read this? Have you noted this? Are you sure? Are you? Great. Now let's go with the certain quick questions. Person who used Boolean algebra for describing the operations of the logic gate first was, yes, he was the Shannon. He was the person who uses Boolean algebra for describing the operation of logic gates. Next, in Boolean algebra, A or B is equals to Y implies that sum of A and B is Y. No, this is not summation. Y exists when A exists or B exists or both. Basically, this plus sign represents the OR, and when we say OR, that is either of kind of situation. So if one of this two is exists, or if one of them is exist, that means it is quite possible that even both are exist. So Y exists when A exists or B exists, or we can say it's a both A and B exist. This would be the correct option. Next, in the Boolean algebra, the following one is wrong. Yes, 1 plus 0 is equals to 1. This is correct. 1 plus 1, 1. 0 plus 1, 1. While 0 plus 0, no, this is not correct. And as they have answered the wrong, this would be the correct answer. I hope this is clear. Is it? Is it clear? Are you sure? Great. So now let's discuss the logic gates, or I should say it's a primary logic gates one by one, and then we will go to the questions based on them. So first we will begin our discussion with the OR gate. We can say an OR gate has two or more inputs with one of them as an output, and the Boolean expression for OR gate, it's a Y is equals to A or B. This is Y equals A or B, and it is having only one concept, that output is 1. Output of the OR gate is 1 when either input A or input B or both are the 1. So if any one of the input is 1, if any one of the input is 1, output is 1. It is the simplest logic of OR gate, that you are having an n number of inputs, but within that n number of inputs, if only one of the input is 1, then the output will be 1. That's it. Then don't bother about that the rest of the n minus 1 number of inputs. Yes, if none of them is 1, then the output would be 0. It is as simple as that. So let's understood these are the inputs and this will be the outputs. So when I say these are the inputs, this is the output. We have two inputs, one of them is the A, another is the B. and the on an output side it is equals to A or B. This is equals to Y. So when we provide both 0 0, then the output will be the 0. When we provide a 1 comma 0, then the output will be 1, because any one of the input is 1. Now when we say it's a 0 comma 1, again output will be 1, because this one is 0, this one is 1. And when input is 1 comma 1, then the output is 1. I hope this is clear. So it is only the concept, if any one of them is 1, if any one of them is 1, the output is 1. It is as simple as that. Let's look at the construction of OR gates by using the diodes. As you can understand that this is the power supply, and you can connect it vice versa to the different circuits. And if you connect it with the different circuits, let's say suppose you have connected with this, and if this has been connected, then this diode D1 will be the forward bias, because this is the PN, as you understand V now, and we are getting the output. Let's suppose if we disconnect it from here, and let's suppose we are connecting it over here, then this is has been not connected. That means this is 0, this is 1, so the output, this will behave as a closed path, and the output would be available at this position. Let's say if both are connected, then this both will be conducting diodes, and when this both the diodes will conduct, that means it is the output will be the available at 1. So basically when we discuss about the OR gate, always consider that this is somehow parallel circuits. Yes, when I say parallel circuit, that means if any one of the path is available, the output would be available. If all the paths are broken, let's suppose if you have not connected it anywhere, something like this, then as on both the sides 0 would be there. And if it is a 0, in the input, output will be definitely 0. I hope this is clear. Is it? So please do remember this, they are somehow parallel circuits. This will help us for sure. Let's look at the quick question. The Boolean expression is blank for an OR gate. Yes, it's an A or B. Next, in a bulb circuit for OR gate, when both A and B inputs are 0, both A and B are open. Yes, this implies that circuit is incomplete and lamp is off. Yes, it is same thing. Yes, that when both this are disconnected, and when this both are disconnected, it means that circuit is not connected, and circuit is not connected, that means current is not flowing, and no bulb will glow on if I have connected a bulb over here. I hope this is clear. Is it clear? OR gate. Have you noted this truth table? Did you noted this truth table? Please note this if you have not noted it. Also, you need to mention, you need to write this. It's an A or B. Did it? Have you did it? Yes, this is the symbol of the OR gate. This is input side and this is the output side. This is the symbol of the OR gate. I hope this is clear. Yes, this is beautifully drawn. Let's have a look. Yes, this is the symbol of the OR gate. Now let's discuss the AND gate. It's a second primary gate. An AND gate has two or more inputs and it is having one of the output. And the Boolean expression for the AND gate is y is equals to A or B, which is A and B. This is the y equals A and B, and the output, which we call as an of AND gate, is 1 only when all the inputs are simultaneously 1. Yes, this is the logic, that if all the inputs are 1, output will be 1. If any one of the input is 0, output would be 0. So this is the tagline. If any one of the input is 0, then the output output will be 0. It is as simple as that. And this is the AND gate symbol. This is A, this is B. Here we can provide the inputs. This is Y. I hope this is clear. Is it clear? Great. Let's have a look at the construction of AND gate and the truth table of the AND gate. First, let's look at the truth table. Then, if I observe the truth table, correctly, then this is 0 0, then the output will be the 0. And if it is the 1 comma 0, again one of the input is 0, that means output is 0. If it is a 0 comma 1, then the output would be 0, because again here it's a 0. If it is a 1 comma 1, then this will be converted to the 1. I hope this is clear. Is it clear? Is it? Are you sure? Are you sure? Do you understand this? Great. Now let's look at the construction of the AND gate by using the diodes. Let's suppose we have connected this, and as you can see, this, as this is connected, this will be the 1. It is disconnected, this is the 0. So the thing is that this is the plus 5 volt and this diode is reverse bias. And as this diode is reverse bias, it is not going to conduct. This is still open, but this is a plus 5 volt. This will complete the path, and at this point this Y will be the 0. Now let's suppose understood that this is closed but this is open now. Yes, this A has been open, so the same situation will occur. That this will form a reverse bias, this will become the forward bias, and again Y would be the 0. Now let's suppose the case is both are connected. When this both are connected, this both are the open path, and if it is open path, then the current will flow from this to this, and this output will be the 1. I hope this is clear. Is it clear? Is it? Great. One very interesting circuit is look like this, that when let's suppose this both switches are there, A and B. Let's suppose if any one of the switches is closed, let's say if only A is closed or if only B is closed, then due to not completion of circuit, bulb will not glow. But if both are closed, then the bulb will glow. You can see this, that A is closed, bulb is off, B is closed, now bulb is on. Yes, both is open, bulb is off. Yes, I hope this is clear. So it is the situation of AND gate, that when both the inputs, or when all the inputs are 1, output is 1. Or you need to remember that if any one of the input is 0, then the output would be the 0. Great. Now let's look at the Boolean expression for an AND gate. That is the Y is equals to A plus B. No, this is for the OR gate. Y is equals to A dot B. Yes, it's a correct one. Next. And blank gate has 2 or more inputs with 1 output. Yes, it's an AND gate. Even this could be the true, that OR gate has 2 or more inputs with 1 output. Yes, it's a multiple correct. Great. Next, let's discuss the NOT gate. So NOT gate has a single input and a single output, and the Boolean expression for the NOT gate is Y is equals to A bar. This is what we call as a A bar. And the output of NOT gate is the inverse of the input, or it performs negation operations. So this is the circuit symbol. Now let's look at the truth table of this NOT gate. This is the construction of the NOT gate. And if we look at the truth table, then if input is 0, output is 1. If input is 1, output is 0. It is as simple as that. Yes. So whatever you are going to provide, it will give you the bar of that. When I say bar of that, if 0 is the input, 1 is the output. If 1 is the input, 0 is the output. It is as simple as that. So this is the NOT gate. The Boolean expression for NOT gate, yes, it's a y is equals to a bar. NOT gate has blank input and a blank output. Yes, it is having a single input, single output. So this all are the primary logic gates. Now we are going to discuss about the universal gates. Basically we are having the two gates as the universal gates. One of them is the NOR gate and another is the NAND gate, as they have been said a universal gates because with the help of NOR and NAND gates we can design any of the gates are of our choice. So that's why these gates are known as the universal gates. Let's begin our discussion with the NOR gate. Basically this is the gates which we can say this is the OR plus NOT. So this is not new to us. This is basically the combination of OR and NOT gate. So it has two or more input and one output. A negation applied after OR gate gives a NOT and OR gate, or simply we can say it's a NOR gate. And the NOR gate output is inverse. This NOR gate output is inverse of OR gate output. And this output of NOR gate, the output of NOR gate is one only when all the inputs are simultaneously 0. The Boolean expression for this, it's y is equals to a plus b whole bar, and this is the schematic of it. And next let's look at this bubble. I hope you can see this. This is the a, this is the b, and this is y, and this is its Boolean relation. It's a y is equals to a or b whole bar. So if input is 0 comma 0, if input is 0 comma 0, let me help you guys, it's an a or b. Then if input is 0 comma 0, output is 0. And if I make a note of this, that means it's an a plus b whole bar, it would be the 1. If it's a 1 comma 0, it's a 1. If I make note of this, it's a 0. If it's a 0 comma 1, it's a or b will give me the 1. Then if I make a note of this, it's a 0. If it is a 1 and 1, then if I make an a plus b, it's a 1, and note of this is the 0. I hope this is clear. So this is the NOR gate. This is the simply NOR gate. I hope this is clear. Let's have a look. It says that NOR gate has blank inputs and blank outputs, two or more inputs and one output. Next, blank gate output is inverse of OR gate output. Yes, a NOR gate output is inverse of OR gate output. So it was the NAND gate, it was the NOR gate. Now we are going to discuss about the NAND gate, which is basically AND plus NOT gate. It is the NAND gate. So NAND gate, basically it has two or more inputs and one output, and a negation applied. A negation, that means the NOT operation applied after AND gate gives a NOT and AND gate, or we can say simply it's a NAND gate. So NAND gate output is inverse, it's an inverse of AND gate output. And the Boolean expression for NAND gate is y is equals to a and b whole bar. It's a or b bar. The output of NAND gate is 1 only when at least one of the input is 0. And the NOR and NAND gates are considered as universal gates like OR, and NOT by using either NOR or NAND gates repeatedly, that we can form OR gates or AND gates or NOT gate by repeated use of NOR and NAND gates. So let's look at the circuit diagram and the symbol. This is the symbol of NAND gate. It is something like this. Yes, this bubble represents the symbol of NOT. So it's let's do this. It's a or B. If it is 0 comma 0, output of A or B would be the 1, and output of A or B and then not operation, it's a 1. When this is 0, sorry, when this is 0, this output is 1. When this is 1 comma 0, this is 1 and 0. If I perform AND operation, it's a 0, and not gate of this, it's a 1. If it is a 0 and 1, if it is a 0 and 1, if I make an AND operation of it, then this will simply give me the 0, and if I make a NOT of this, it's a 1. If it is a case, if it is a case of 1 and 1, if it is a case of 1 and 1, then the output of this A and B, it's a 1. And if I make a NOT operation of this, this will be the simply 0. I hope this is clear. Is it clear? Are you sure? Do you have any doubts? Is there anything? Is there anything? Any doubts? Are you sure? No? Do you have any doubts up till now? Is there anything? No? Great. So the Boolean expression, a Boolean expression for NAND gate, it's y is equals to A or B whole bar. It's y is equals to A B whole bar. Next, our NAND gate output. NAND gate output is inverse of blank gate output. Yes, NAND gate output is inverse of the AND gate output. So this was all about the NAND gate and NOR gate. Now we have two more gates, and they are generally called as the supplementary gates. They are the supplementary gates. One of them is the XOR gate, and second, it is the XNOR gate. Let's look and study them one by one. First, let's begin with the XOR gate. So when I say XOR gate, it is basically the symbol of the XOR gate. It is something like this, that this is the inputs and this is the output. The Boolean algebra for this is y is equals to A bar B plus A B bar. This is the Boolean algebra of the XOR gate. So let's try to derive the truth table for the XOR gate. Let's work on it. So let's suppose make some columns. It's an A, B, let's say A bar, B bar, it's A bar B, A B bar, and last is the output. So let's suppose if I am having a 0 comma 0, 0 comma 1, 1 comma 0 and 1 comma 1 as the inputs, then if I make an A bar of this, then 0 will work as a 1, 0 1 1 0 1 0. I hope you understand what I'm doing. Now it's a B bar, that means not of B, it's a 0 1 1 0 0 1 1 0. Great. Now it's a turn for A bar B. So I want to perform AND operation of this 2. When I want to perform AND operation of this 2, this 0 comma 1, it's a 0, 1 1, it's a 1, 0 0, it's a 0, 1 A bar and B, 0 in 1, it's a 0. Yes. Now it's an AND operation. Now it's an AND operation of A and B bar. This 2 column, you need to perform AND operation. That means if any one of the input is 1, output is 1. If one of the input is 0, output would be the 0. So now A and B bar, this is 0, this is 1, this is 0, this is 0, this is 0, it is 0, this is 1, and sorry, it's an AB bar. This is 1 and this is 1, this will be the 1. This is 1, this is 0, this will be the 0. And at last this is Y. That means the I have produced this A bar B. I have produced this AB bar. Now I need to perform OR operation between this two. That means if any one of the input is 1, output will be the 1. So it's a 0 comma 0, it's a 0. 1 0, it's a 1. 0 1, it's a 1. 0 0, it's a 0. I hope this is clear. So this is the truth table of XOR gate. Yes, you need to at least remember this. If you look at this and observe this very carefully, the output is 1 when input is 0 and 1. The output is 1 when input is 1 and 0. So basically this is what we call as an inequality detector. When I say it's an inequality detector, that means the output of the circuit will be 1 when inputs are different. If inputs are same, they are the 0 0, output would be the 0. If they are the 1 1, output again would be the 0. So this is what we call as an inequality detector. This is equals to Y is equals to A bar B plus AB bar. I hope this is clear. Would you like to show the circuit diagram for this? Would you? Let's have a look. This could be given as this is A, this is B, and let's see what my Boolean algebra is. It's a Y is equals to, it's an A bar B plus AB bar. So let's design one NOT gate over here, and this will work as the A bar, and let's design a B bar over here. So this is the situation that this is the B and this is the another gate. So let's connect this A, and I need to connect this B bar over here. This is B bar, and this B has been already connected, and this is the A bar. Yes, and as this is A bar B and AB bar, now I need to connect this with the OR gate so that I can get this. It's an A bar B, AB bar, and OR operation. Yes, this is the Y. It is as simple as that. So now you can understand this, that this is A. So if you keep moving, this will give me the A. This is the NOT gate is there, so this is A bar, and this is the A bar. This is the B, and this is the B bar, and it will be at here. So this is basically an AND operation of A and B bar. This is basically an AND operation of A bar and P, and I'm performing OR operation of this two. That means it is the final output. I hope this is clear. Is it clear? Do you understand this? Have you got this? Are you sure? Great. So any doubts? No? Great. So this was XOR, and we have been left with one more gate, which was XNOR gate. So basically this XNOR gate is the XOR gate plus NOT gate. So if I look at the Boolean algebra of it, it's Y is equals to A bar B plus AB bar whole bar. So whatever the output will be, just connect it to the NOT, and that will convert itself. It will convert itself to the XNOR gate. I hope this is clear. Was it clear? Great. Symbol of it is something like this. Yes, this is A, B, and y. This bubble represents XOR plus not. And if I go for the truth table of this, it's an A, B, and Y. This could be 0 0 0 1 1 0 1 1. Then if it's an XOR, this will be the 0. This is basically XOR plus not. So this is 1, this is 0, this is 0, this is 1. So now again, if you look at this carefully, this is known as the equality detector. This is the equality detector, that if both the inputs are same, when both the inputs are same, output would be the 1. If it is 0 0, output is 1. If it is 1 1, then the output is 1, and so on. So is it clear? Is it? Do you understand this? Have you understand this? Did you get this? Are you sure? Do you have any doubts? Is there any doubts, any confusion over this? Anything? Any doubts? Any confusion? Are you sure? Do you understand this completely? Have you got this? Great. So this is the equality detector for us. I hope you understand this. Have you? Great. So are you ready for the numericals based on this logic gates? Are you? Can you do this? Can you? Are you sure? So let's begin our numericals. Let's look at this. They have given us the diagram something like this, that this was the situation. Please draw this with me. This is A, this is B, and this is Y. It said that the given electrical network is equivalent to which gate? So they have asked about this, that the given electrical network is equivalent to which gate. So what we understood is that, let's look at this. This is probably new to you, that both the inputs has been connected with each other and it has been supplied as two inputs. So when this would be the situation, let's have a look. A bubble is there. Yes, let's suppose I have pass on 0 over here, then this is 0, this is 0, because both are connected. And the when I apply 0 and 0 to the OR gate, it will give me the 1, and 1 would be bubble, then it would be a 0. If I apply 1 comma 1, if I apply, that means 1 over here and 1 1 pass on over here, so then I have made a mistake. So if I let's redo it. If I apply a 0 over here, then it will pass on 0 and 0 over here, and the output of this 0 and 0, output of this 0 and 0 is the 0. And when I apply this 0 to this NOT gate, the final output would be the 1. Now let's understood that when we apply a 1 over here, then it will pass on 1 comma 1 over here, and when we pass on 1 comma 1 over here, our output will be the 1. And when we NOT it, it's 1 comma 0. So basically this is the simply NOT gate. Yes, even same thing is true for the NAND gate also. Look at this. If this is the NAND gate and both of inputs has been connected, if both of the inputs of the NAND gate has been connected, then it would look like this. Let's suppose I will pass on 1, then 1 comma 1. Yes, this 1 and 1 to the end, and when we apply 1 and 1 to the end, this will be the 1 again NOT gate, it would be the 0. Next, let's say we are applying 0 over here, then it's a 0 and 0. And if it's a 0 and 0, then the end operation will give me the 0, and 0 to not, it's a 1. So again it is somehow the NOT gate. I hope this is clear. Do, do you understand this? Have you? Have you got this? Any doubts? Is there anything? Any doubts? No? One more thing. We will back to this question. That is what we call as a bubbled gate. And when I say bubbled gate, it is something like this. Let's suppose it is something like this. So when you apply a 0 comma 0 to this, then this is simply the cases of something like this. This bubble represents the NOT, and this is the AND gate. Let me redraw. Yes, and it is something like this. Yes. So if I apply 0 comma 0 over here, 0 to the 0, this 0 will apply to the NOT, it's a 1. 0 to the 1, 1. 1 1, it's a 1. 1 to the NOT, it's a 0. If I apply 1 comma 1 over here, then this 1 1, it's a 0 0. 0 0 up to the AND gate, this is 0, and 0 to 1, it's a 1. So when I have applied a 0, the output is 0. When I have applied 1 1, it's a 1. Yes, it's a 0 comma 0, it's a 1 comma 1. When I'm applying, it's a 0 comma 1, let's say, then 0 to that, 0 to not, it's a 1. 1 to that, 1 to not, it's a 0. It's a again 0 0 to 1. So if a 0 to 1, it's a 1. It's a 1 to 0, it's a again 1. I hope this is clear. So which truth table it is? This is the truth table of OR gate. I hope this is clear. Is it clear? Is it? So this is bubbled AND gate, which will behave for me as an OR gate. Or you can simply find out this. This is keep interesting. This is A, this is B. If I make a NOT of this, it's an A bar. This is B bar. And I'm going to again perform the AND operation. Then it's an A bar and B bar, AND operation. This is the AND operation, and then again NOT gate. So it's something like this. So as when we discuss the Boolean De Morgan's theorem, we used to discuss that this is the A bar and B bar whole bar. This is equals to A or B. It is something like this. A same way if I understood that this is the bubbled OR gate, which can behave as an AND gate. So this is bubbled OR gate, which can behave as the AND gate. I hope this is clear. So let's back to the question that we were supposed to discuss. That this was the circuit diagram. Yes. So this is A, this is B, and as it has been connected with the OR gate, so this will give me an A or B. Then it has been connected with the NOT gate. It's a plus B bar. Again it's a NOT gate because this construction works as a NOT gate. So this is A plus B bar whole bar, which is again equals to A plus B. Now again it has been connected to the NOT gate. This is simply the A plus B whole bar, which is NOR gate. I hope this is clear, and that has been done. This is one of the approach. If you know the Boolean algebra, this is the quickest approach. If you don't know this, what you are supposed to do is that apply the different combination A, B, Y, and this combination could be 0 0 0 1 1 0 1 1, and find out the values. It's according to the truth table. that if it is a 1 1 to the OR gate, then the output will be 1, then I will perform an NOT operation and all that blah blah blah. Yes, then just try to identify which gate is it. I hope this is clear. So do you understand it? It is a comparatively longer approach. So just try that you can remember the Boolean algebras. And if we know the Boolean algebras well, if we know the Boolean algebras well, the things would be much easier. I hope this is clear. Is it clear? Is it? Are you sure? Are you? Great. One more question based on this. Let's have a look. The question is something like this. Yes, this is A, this is B, this is Y. They said the adjoining logic symbol is equivalent to. What does it represent? So if I make understand, this is A, this is B, this is AND operation, so it's an A and B. Then it's a NOT operation, this is A and B, it's a NAND technically. And we now understand that this is not, so it's an A dot B whole bar, which is equals to A dot B. That's it, you did it. So basically it's an OR gate. Sorry, it's an AND gate. I hope you understand this. So Boolean algebra, that is must to learn, because it will reduce the time drastically. Yes, so time to solve the question will reduce to almost 10 to 15 seconds if you know the algebra. And even if you don't remember the complete Boolean algebra relations, please go through at least the De Morgan's theorem. And this De Morgan's theorem will help you guys a lot to do this very quickly. Great. Now let's discuss the second digital blocks, which are very important. They are the integrated circuits. Let's discuss integrated circuits. The conventional method of making circuit is to choose components like diodes or transistor, resistors, inductors, capacitors, etc. And we are connecting them by soldering wires in the desired manner or according to our circuit diagram. In spite of this, miniaturization introduced by the discovery of the transistors, and such circuits were still bulky. So when we want a certain different logic, a certain different aspect, that because the circuits are bulky and that cannot be accommodated into a smaller space. So what we have came to a new concept, which says that concept of fabricating an entire circuit on a small single block or a chip of a semiconductor has revolutionized the electronics technology. And such a circuit is known as the integrated circuits, which we call as an IC. And it is the most widely used technology is the monolithic integrated circuit. As you can see this, that they are the different sockets, and they are the chip holders, they are the relays, and this is the copper tracks, and we are going to hold this on this green board. That is what we called as the boards or circuit boards. Yes, so the word monolithic is a combination of two Greek words. Monos means a single and lithos means stone. So this in fact means that the entire circuit is formed on a single silicon crystal, or we can say chip. And the Chip dimensions can be as small as 1 mm cross 1 mm, or even it could be smaller than this. So depending on the nature of the input signals, ICs can be grouped into the two categories. One of them is the linear or analog ICs, and the another one of them is the digital ICs. The linear ICs processes analog signals which changes smoothly and continuously over a range of values between a maximum and minimum, and the output is more or less directly proportional to the input, so it varies linearly with the input. And one of the most useful linear IC is its operational amplifier, which generally called as the op-amp. Yes, it's a 741, is it is the number of it, it's an op-amp. The digital ICs processes signals that only have two values, and they generally contain circuits such as the logic gates. So depending upon the level of integration, the ICs are termed as the small scale integration SSI, generally logic gates less than or equals to 10. Medium scale integration, which we call as an MSI, generally less than or equals to 100 logical gates. The large scale integration LSI, generally less than 1000 logic gates. Very large scale integration, which is a VLSI, logic gates generally greater than 1000. So this is the technology of fabrication is very involved, but large scale industrial production has made them very inexpensive. As well as the biggest advantage of this ICs is their their availability in smallest size, because as you understand that what would be the size of the mobile phones when they have been launched in up, and when they came to an India initial level, and whatever the size of the mobile phones now we are receiving, that it is having much larger facilities, much more advanced features, but almost of same size. Even it was the trend and between era that there is a very small mobiles were available, that it hardly weighs around less than 50 grams. So this is the capability and this is the strength of this integrated circuits. I hope you understand this. Let's look at this quick questions. In an integrated circuits, the word monolithic, yes, means it's a single stone. Mono stands for single, and lithic, it's a stone. Next, the linear ICs process blank signals which changes smoothly and continuously over range of values between minimum or maximum to the minimum. Yes, they will process the analog signals. I hope this is clear. So let's wind up this session over here. This was all about the logic gates, but if you go through the previous year asked questions, you will definitely find at least one question on each paper of each year. So this is very easy to do fasting, and second, it will take less than 10 to 15 seconds of your time to get it done for each question, every question. So please go through this very carefully, because this are the questions which can earn for us. I hope you can understand the meaning of it. So please go through this, please practice a lot this kind of questions, and this is very easy as well as this is fun making questions. So please go through it. This will help us to get it done, to crack our examination very easily. Thank you. Have a good day. Take care.